Hello and welcome everybody. This series of videos is about section 4.2.2 of the book, where we will learn how to use Markov chains to compute Monte Carlo estimates. So that builds on the Metropolis-Hastings algorithm we have learned about in the previous videos. And the output of this algorithm is the Markov chain xj. And these xj we will now plug into a quite standard looking Monte Carlo estimate and see what we get. And there are in the book two sections about this topic. 4.2.1 has the theoretical aspects, and I will not produce a separate video about this, and we are just skipping this here. And instead we'll focus on section 4.2.2, which has practical considerations you need to keep in mind when doing that. So after watching these videos, you should be in a position where you can use Markov chain Monte Carlo methods. But if you want to learn more about the theory, you could go and read section 4.2.1 on your own. Great, so let's jump in. This video is about convergence of Markov chain Monte Carlo methods. And the topic of these videos is that we now finally are in a position where we can consider Markov chain Monte Carlo estimates, and I've already explained this. These are estimates which look like normal Monte Carlo estimates, but the new thing is that xj is now a Markov chain, and that is chosen so that the stationary distribution equals the distribution of x. And the last section we spent to discuss how we get such a Markov chain. So xj will be produced by the Metropolis-Hastings algorithm. And for the Metropolis-Hastings algorithm, we need as input a target distribution, which are called pi there. And here we will use the distribution of x. And the question is then, do we still have this property that the Markov chain Monte Carlo estimator is close to the expectation of f of x? So that question is what we'll address in this series of videos, and it's the topic of section 4.2. So before we jump to section 4.2.2, I want to just quickly discuss section 4.2.1. We'll not cover this here, but I will give you a very short summary. So turns out the answer to this question is that a Markov chain Monte Carlo close to the expectation of f of x depends on the Markov chain xj. So sometimes what we have is enough, most of the time, but sometimes it's not. And the key thing to know is that for this to work, the Markov chain xj needs to explore all relevant bits of the state space. So where f is non-zero and where x can take values, we need it so that the Markov chain can actually go there. So for that relation to hold, x must visit, I write a bit informally here, relevant parts of the state space. And what I mean by this is, let me come back to an example from earlier. If this is pi, similar to what we had before, then you see pi has mass here and has mass here. And we have seen earlier that if we do random walk metropolis, we need to be a bit careful with the choice of the sigma, the variance of the increment. And if we get this right, then we will get some samples here and some samples here, and the method will work. So it will jump between these two modes from time to time. It will see both of them, and the estimate based on the xj, so where xj here are the samples which are sometimes in the left mode and sometimes in the right mode, that should converge to the true expectation here. But we saw examples where sometimes the Markov chain doesn't make it across this gap in the middle. And in this case, we would be in a situation like this, where there are just more and more samples accumulating here, more in the middle, a few in the tails, but it could happen that the Markov chain doesn't make it over to this mode on the right. And in this case, the estimate computed from that would not correspond to the full expectation of f of x, but instead would correspond only to this part. For example, if we say f is identity and we just try to estimate the expectation of x, that would then come out somewhere here, where really the expectation of x will be somewhere here because both modes have mass and it should be somewhere in the middle. So that kind of errors can occur. And this criterion must visit all relevant parts of the state space. That is formalized in section 4.2.1, and there you can read some actual theorems which tell you conditions under which the estimate here is guaranteed to converge to the correct value as n goes to infinity. But we'll not cover this here, and for practical applications, most of the time the intuition which comes from this picture is enough, so we must be sure xj, the Markov chain, can reach all parts of the state space where x has mass. So if there are different modes, it must be able to cross between the modes, and if x is spread out, then the Markov chain must be able to go everywhere, though that means we must have proposals which allow it to reach everywhere. And often you can assess this with the help of pictures. If you draw a plot, like in a one-dimensional situation, you could plot pi, and you could plot your samples, and you will immediately see if you run into this problem. And in the two-dimensional situation, you could still do that, only you would do a scatter plot with dots in a two-dimensional plane, and you could maybe plot level sets of pi, but in higher dimensions, that is a real problem to assess whether you have explored all space or not. So this is one of the challenges if you use Markov chain Monte Carlo estimates. You need to understand a bit about your target distribution pi, so you need to understand a bit about this x, in order to make sure your Markov chain does the right thing. Good. So let's leave our discussion of section 4.2.1 at this, and now let's jump straight in for section 4.2.2. The first concept we need to discuss is the bias of these estimates. And different from standard Monte Carlo estimates, it turns out Markov chain Monte Carlo estimates are biased. We have pi is a stationary distribution of the Markov chain. And that means if x0 was distributed according to pi, then xj would also be distributed according to pi for all j in n. And in this case, we would have all xj have the same distribution as x does. Pi is still the distribution of x. So we would know the expectations are also the same, so that would equal expectation f of x. And then we can get, as before, expectation 1 over n sum j from 1 to n f of xj. That is our Markov chain Monte Carlo estimate. And this we know is 1 over n sum j from 1 to n expectation f of xj. So that would be expectation f of x in this case. So that's what we had for standard Monte Carlo estimates. Now, in our case, for Markov chain Monte Carlo estimates, that is no longer true like this, because the problem with this argument is this part here, where we say x0 is distributed according to pi. Namely, if we could make this so if we could generate x0 correctly with distribution pi, then we could just as well use a Monte Carlo estimate. We should do that then, because for a Monte Carlo estimate we need samples distributed according to pi. That was how Monte Carlo estimates work. So if we could generate x0 like this, we should use Monte Carlo estimation instead, because we will see later that is more efficient and has easier theory, but only if we can generate the samples. So what we need to do here is we need to assume that x0 is not distributed according to pi. And if you think back to the algorithm, we just said x0 we can pick however we like to. The only constraint coming from the Metropolis-Hastings algorithm was pi of x0 must be positive. But we did not require it to be random, and we did not say it must be distributed according to pi. So what we need to assume is x0 does not satisfy x0 is distributed according to pi. Then one can show, here we do that just intuitively, but one can formally show that often the distribution of xj at least converges to pi as j goes to infinity. And then we can conclude for large j that will already be close to pi. And in this case, what we get is the expectation of f of xj, since xj has a distribution which in some sense is close to the distribution of x, will be approximately equal to expectation of f of x, and this will get closer as j increases. To show when this statement is true formally, one would need to know much more about Markov chain than we are assuming here, but it will require some version of the Markov chain being irreducible and aperiodic, and the formal conditions are, for example, satisfied if you use random walk metropolis with normal distributed increments, like we did in the previous videos. So let me just write this. This is, for example, true if xj comes from the random walk metropolis algorithm with increments which are normally distributed. So that's the most common case, and in this case one can formally prove that that holds. And in this case then we can conclude for large j the distribution of xj is not exactly equal to pi. So that's what we concluded previous slide, that we could write as distribution of xj equal to pi, and then we could conclude the expectations are exactly equal. Here the distribution of xj is close to pi, and therefore the expectations are approximately equal. And then if you continue the argument where we work out the expectation of the Markov chain Monte Carlo estimates, then what we find is expectation of Zn MCMC is expectation of the average of samples, the average of the expectations. And now each of these is approximately equal to the expectation of f of x. So the average will be approximately equal to expectation of f of x. This is in contrast to exact equality, which we had earlier if we assumed we start the Markov chain with pi exactly. So, and if we have this, then we can conclude the bias of the Markov chain Monte Carlo estimate is difference between the expected value of the estimate and the value we are interested in, so the truth, that's expectation of f of x. And if these values are similar to each other, then the bias is approximately equal to 0. But that is less good than it was for standard Monte Carlo estimates, because there we had exact equality and here we have approximate equality. And that matters because the bias is part of the formula for the error. So the mean squared error of Zn Markov chain Monte Carlo we know equals the variance of Markov chain Monte Carlo plus the bias of the estimator squared. And before this term did not contribute, whereas now it does. It's small, but it's non-zero. So we need to worry about the bias this time. And what one does? Well, the bias came from here, so we need to look what's going on here. So one thing one can do is we said this difference here gets smaller as j increases. So at the beginning we may be different, but we converge to pi, so that should get better and better. And for this reason, one thing which is commonly done is to throw out the first samples. So if you do, I don't know, 1,000,000 steps of the Markov chain, you may want to throw out the first 10,000 or 100,000 samples, just because there this difference may still be larger than for the rest, and then these terms may contribute more to the bias. So that is one standard way to keep the bias small, and I'll write that down in a second. The other thing I should say here, I wrote this convergence holds often, and it holds for the random walk metropolis algorithm with normally distributed increments. And I just should point out that result is technically true, but it says nothing about the speed of this convergence. So this convergence can still be very, very slow. So you need to also make sure, if you can, to construct a Markov chain which explores the state space fast enough. So in this example, what we need is we need for the Markov chain to jump between the modes often enough that there are enough samples here and here, and that it's balanced, and that we have seen everything X can do. So if you think you generate 1,000,000 samples, but it takes, say, 800,000 steps until the process jumps over for the first time, that is not fast enough, because then you have 800,000 samples here and 200,000 samples here, just because it took so long until we got here. And so the estimator will wrongly assume most of the time the process is here, when if you look at the shapes I drew, they have roughly equal area, so both modes should have roughly the same probability. So that would be an example where the process moves too slowly. So we need to make sure if they are modes that they are all visited often during our sampling period. And that is the other mitigation for the bias. If the process moves through the state space fast enough, then that convergence will be fast, and then these errors will be small for most of the J's, and then the bias will also be small for the whole estimator, which incorporates all samples. So that's the second mitigation. We have what's called a burn-in period, where we throw out a fraction of the samples at the start. And we need to be careful when we construct our Markov chain to make sure it explores the state space quickly. It cannot get stuck in corners or in modes or somewhere for long periods of time. So let me just write this. So there are two ways to keep the bias small. And one is we need to be sure that the Markov chain explores the state space fast enough. And that is a matter of choosing good increments, for example, in the random walk metropolis method. So we can do that. The second idea is we can use what's called a burn-in period. And I said this, so what we do is when we compute these estimates, then we take the sum normally over all samples. And if we use a burn-in period, then instead we throw out the first m samples. So we would start at sample m plus 1 and go to the end. And then when we compute the average, we no longer need to divide by n, but instead to keep it an average, we need to divide by how many samples did we use. And that is now n minus m, because we ignored the first m. So then we would compute the Markov chain Monte Carlo estimate using this modified formula. And the first m samples are the ones where the bias is largest, and hopefully that is enough to bring the bias down to a reasonable level. So this finishes the first video in the series, and in the next video we'll look at the variance of the estimator with the aim of combining what we just learned about the bias with the new results through discussing mean squared error. So see you in the next video.